Dear students, in this video, we are going to discuss about rotational motion. So we will discuss the comparison between linear motion and rotational motion, and we will describe the role that quantities play in linear motion. What other quantities can you expect to play the same role in rotational motion? So, to begin with, we know that in linear motion, mass plays a very crucial role. Like, mass decides the amount of force that you would need to apply to move the object. Like, if the body is more massive, you need to apply more force to make it move. So in linear motion, mass is a measure of inertia of the body. Like, more the mass of the body, more will be the inertia. But now we are going to discuss that in rotational motion, what is the quantity which plays the same role as mass plays in linear motion. Like, if you are discussing the inertia of some object in rotational motion, so how to describe that inertia in rotational motion? So in order to do that, we need to study moment of inertia. Just like mass tells you the amount of force to be applied on an object to move it in a linear motion, the same way moment of inertia decides the amount of torque that you would need to apply to move the body in rotational motion. So to begin with, we have the derivation kinetic energy of rotation. Okay, so suppose there's a body which is rotating around a fixed axis. I repeat, there's a body which is rotating around a fixed axis. So if that body is rotating, all the particles that are constituting this body, they are also rotating. It's as simple as that. So they are moving with linear velocities v1 vector, v2 vector, and altogether the body is rotating with a common angular velocity omega. And this is the axis of rotation. Now, when you talk about the distribution of particles in this body, suppose mass m1 is r1 vector away from the axis, suppose m2 is r2 vector away from the axis. So this way, what do we know? That basically all the particles are situated r1, r2 and so on distances away from the axis, and the whole body is rotating with the angular velocity omega. Okay, so v1 equals to r1 omega, v2 equals to r2 omega, v3 equals to r3 omega, and so on, right? So how to calculate the kinetic energy of all the particles which are moving? So kinetic energy of first particle will be half m1 v1 square. Otherwise, kinetic energy is half mass into velocity square. But when you talk about the first particle, it will be half m1 v1 square. When you talk about the second particle, it will be half m2 v2 square, half m3 v3 square, and so on, right? But we know that this expression has been written in terms of linear velocities. But since we are considering rotational motion under consideration, so it's better to write the whole expression in terms of angular velocity. And we know that v1, see, linear velocity is related to angular velocity by the relation v is equal to r omega. So v1 equals to r1 omega, v2 equals to r2 omega, v3 equals to r3 omega. I told you that the entire body is rotating with a common angular velocity. So I have not taken omega 1, omega 2, omega 3, right? So in place of v1, I have written r1 omega. In place of v2, I have written r2 omega. In place of v3, I have written r3 omega. And what can be taken common in this expression? 1 by 2 from the initial side, and then you are left with m1 r1 square, m2 r2 square, m3 r3 square, and so on, omega square. So this is the kinetic energy of rotation. Like, what kinetic energy is involved when the body is rotating with the angular velocity omega. So this whole expression m1 r1 square m2 r2 square, instead of writing this big expression, I am naming this expression as I. So this is I, where I was substituted in place of all these things, right? All this quantity. So with this is equal to summation I is equal to 1 to n mi ri square, where I runs from 1 to n, like m1 r1 square plus m2 r2 square plus m3 r3 square and so on. So, you know what you have just proven? See, this is the expression that you got as kinetic energy of rotation. And when the body is in linear motion, its kinetic energy is given by half mv square. So, I know that in place of linear velocity v, I have angular velocity omega in rotational motion. This is for linear motion, this is for rotational motion, right? But in place of m, mass, I am having I. So this means the role that mass plays in linear motion, the same role I plays in rotational motion. So I is known as moment of inertia, right? It plays the same role in rotational motion as it is played by mass in linear motion. Now we will discuss about the physical significance of moment of inertia. We know that moment of inertia is given by mi ri square summation, which means that it is simply equal to mass of a particle multiplied by the square of its distance from the axis, right? And if you see that kinetic energy came out to be half into I into omega square. So what is I? It is equal to 2 into kinetic energy when omega is equal to 1. If you take omega is equal to 1, so I becomes equal to twice of kinetic energy. So its physical significance is restricted to the fact that it measures the inertia in rotational motion. And what are its units? Since it is equal to mi ri square, so its units are mass into distance whole square. Mass is measured in kg, distance whole square is measured in meter square. So kg meter square is the unit of moment of inertia. This is the SI unit. And when you talk about the CGS unit, of course mass is measured in grams and distance is measured in centimeters. So yes, gram centimeter square is the CGS unit of moment of inertia. And when you talk about the dimensional formula, that has to be ml square T0. So yes, this is all about moment of inertia. I repeat few of the aspects, that moment of inertia is something that would tell you how much torque you need to apply to rotate a body. Like mass tells you how much force you need to apply to move the body in linear motion or to stop a moving body. So mass is a measure of inertia in linear motion, whereas moment of inertia tells you the torque that is needed to be applied in rotational motion. And both of them are different. Always remember this, because when you want to move a body in rotational motion, no, so it matters what amount of force you are applying and where you are applying the force. Like here, the body is not rotating. Here, the body has shown a curve and it might rotate. So yes, when we are going to consider the rotational motion, we need to consider this fact that it doesn't only matter how much force we are applying. It also matters where we are applying the force, right? So what is the rotational analog of force in this is torque, and what is the rotational analog of mass? It is moment of inertia.